Good morning everyone. Today we will have a tutorial present for our subject DAE11203 circuit analysis. First and foremost, let me introduce my group members. Russell, the matrix number is AA251841, and Kokheng AA250938, and Danish Haikal AA250980, and me, Ding Hui Yi, AA250876. For my part, I will present question 6, which in chapter 1, which is to determine the total power developed in the given circuit. First, we analyze the circuit and calculate the power for each element using the formula P equal to VI, where P is power, V is voltage, and I is current. Next, we apply the passive sign convention to determine whether each element was absorbing or supplying powers. If the current enters the positive terminal of an element, it absorbs powers. If the current enters the negative terminal, it supplies powers. After identifying each element, we calculate the power one by one and then add all the absorbed power together and all the supplied power together separately. After completing the manual calculation, we build the same circuit in PSpice using the given circuit values. We then run the simulation to obtain the power of each element. The simulation result is very close to our manual calculation, showing that our calculation method is correct. So, the most important step in this question is correctly identifying whether each element absorbs or supplies powers by applying the passive sign convention. After calculating the power of every element using P equal to VI, we sum all the absorbed power and all the supply power separately. We found that the total supply power is equal to our total absorbed power, which satisfies the law of conservation of energy. The PSpice simulation also produced a very similar result, which further confirmed that our manual calculation is accurate. So in conclusion, both the manual calculation and the PSpice simulation are consistent. So this confirms that our calculation is correct and that the circuit follows the law of conservation. Thank you.
Okay, Assalamualaikum and hi, my name is Muhammad Nishaka bin Mat Fuad, nama matric AA250980, and today I will presenting our analysis on chapter 2, which is resistive circuit, that focusing specifically on the problem presented in question 9. So in this circuit diagram, as you can see on the slide, we are given a 20 volt independent voltage source connected to a network consisting of 4 resistors, which is a 5 ohm resistor, a 10 ohm resistor, a 4 ohm resistor, and a 6 ohm resistor. So our main objective for this specific problem is to systematically find the node voltage, the branch current I flowing through the rightmost side of the circuit, and ultimately to calculate the exact power absorbed by the 4 ohm resistor. So to accomplish this confidently, we will walk through our step-by-step theoretical manual calculation and then validate those findings directly against a computerized circuit simulation. So moving on to the next slide, we have a side-by-side view of our manual mathematical derivation and our software simulation result in PSpice. So looking at the manual calculation on the left, we begin by finding the parallel equivalent resistance of the 10 ohm branch in parallel with the series combination of the 4 ohm and the 6 ohm resistor, which simplifies beautifully to 5 ohm. So by applying the voltage divider rule across the network, we found that the node voltage is exactly 10 volt. So from there, we calculate the current passing through the 4 ohm resistor by dividing that 10 volt node voltage by the total branch resistor of 10 ohm, yielding a current of 1 ampere. So using the power formula, which is the P equal to I square R, we determine the power absorbed by the 4 ohm resistor to be 4 watt. So if you look over at the right side of the slide, we show our PSpice simulation result that netlist output perfectly mirrors our work. So the node voltage at N00131 is logged as 10 volt and the current through the voltage source is negative 2.00 ampere, meaning 2 ampere is being supplied and the total power dissipation of the system is registered as 4.00 times 10 power of. So finally, let us look at our comparison and discussion slide. So as listed in the comparison table, both our manual calculation and PSPice simulation yield an identical value of exactly 4 watt for the power absorbed by the 4 ohm resistor, which verifying our analysis precision with zero deviation. So diving into the circuit power analysis, the manual calculations and simulation results are highly consistent, which is the 20 volt source supplies a total of 40 watt of power, which perfectly matches the simulation total power dissipation reading of 4.00 times 10 power of 1 watt. So this exact match proof that the total power supply perfectly balance the total power dissipated by all the resistors in the network, validating the fundamental law of conservation of energy. So in conclusion, because our theoretical model using equivalent resistance and voltage divider methods align flawlessly to the decimal point with the software simulation, we have verified that the branch current and the node voltage were determined without error, ensuring a high level of accuracy in understanding this resistive circuit behavior. So moving into chapter 3 on circuit analysis, we are tasked with solving question 12, which presents a classic bridge network powered by a 30 volt independent DC voltage source. So the objective of this problem is to determine the total source current denoted here as IO, which leave the positive terminal of the power supply and travel through a 2K ohm series resistor before splitting into the bridge structure. So the bridge itself is composed of two upper arms containing a 6K ohm resistor, two lower arms containing 4K ohm resistor, and a central shunt branch holding a 2K ohm resistor. While the question prompts us to evaluate this using mesh analysis, so we will explore how a delta to Y structural transformation simplifies of our mathematical journey and verify our calculated value of IO using a comprehensive software simulation tool with PSPice. So on slide 9, we examine the direct correlation between our theoretical derivation and computerized modeling. So we simplified the complex bridge by transforming the top delta network made of the two 6K ohm resistor and the central 2K ohm resistor into an equivalent Y network. So this yielded a top Y resistor RA of 2.57K ohm and two side resistor RB and RC of 857 ohm each, that allowing us to collapse the remaining network into a series parallel combination with an equivalent resistance of RP of 2.4K ohm. So adding the initial 2K ohm resistor result in a total circuit resistance RT of exactly 7K ohm, is giving us a final source current IO of 4.286 milliampere via Ohm's law. So when we look at the right side of the slide showcasing our PSPice schematic, the software confirms our calculation with absolute precision that the source current is registered at 4.286 milliampere and even current split of 2.143 milliampere move down each branch, and 0 ampere flow through the central 2K ohm resistor, and the total system power dissipation is clocked at 1.29 times 10 power of negative 1 watt or 128.58. So concluding chapter 3, slide 10 offers our structure comparison and discussion. And our comparison matrix highlight a flawless match where both the manual calculation and the PSPice simulation deliver a source current of exactly 4.286 milliampere. So this outstanding consistency proof that transforming the bridge into a series parallel network with an RT equal to 7K ohm is theoretically robust. So furthermore, by looking at the identical arm ratio of the bridge where the left side ratio of 6K ohm and 4K ohm perfectly matches the right side ratio of the 6K ohm, 4K ohm. So we mathematically demonstrate that this is a perfectly balanced Wheatstone bridge. Because it is balanced, the potential difference across the central resistor R4 is zero, which our PSPice simulation elegantly verifies by reporting exactly 0 ampere, passing through it and showcasing a perfectly symmetrically 2.143 milliampere split down the parallel path. So ultimately, this exercise successfully verifies that the central bridge resistor does not affect the total current raw, validating our analytical design tools and ensuring high accuracy in matching engineering theory with a computer-aided design simulation.
Today everyone. Today I will to present about for two circuit problems and verified using manual calculation and also PSpice simulation. So starting with chapter 4 on network theorems, let's look at the question 2. So for question 2, our objective here is to determine the output voltage V0 across the 5 ohm resistor using a superposition principle. The circuit consists of 3 independent sources. First is a 12 volt voltage source, and second is a 2 ampere current source, and third is a 19 volt voltage source, and the expected target answer given is negative 125 millivolt. So to solve this using superposition, we analyze the individual impact of each independent source by turning off the other two. Remember, when turning off a source, voltage source are replaced with short circuit, but the current source are replaced with open circuit. So by executing nodal analysis for each isolated case, we find the individual contribution V0. So the 12 volt source alone contribute plus 2 volt. The 2 ampere current source contribute negative 7.125 volt, and the 19 volt source contribute 5 volt. So assuming these values together, so we're using 2 volt minus 7.125 volt plus 5 volt give us a total V0 of minus 1.25 volt, which precisely equals negative 125 millivolt. Alright, so to validate our manual mathematical approach, we model the exact network configuration in PSpice. Here on the screen, you can see our schematic with the bias point enabled along with the raw output data file. By measuring the node voltage on both sides of our target 5 ohm resistor, labeled here as node 100, 190 and node 246. And after that, we got 8.05 volt and 8.175 volt respectively. So to subtracting the right node from the left, and after that will give us our simulated differentiation voltage. So the final answer is also negative 125 millivolt. Alright, so comparing our findings, the manual calculation perfectly matched the PSpice simulation at exactly negative 125 millivolt. So what does the negative value actually tell us physically is it signifies that the actual polarity of the voltage drop is reverse relative to the original assumption, and the right node sit at a higher potential than the left node. So this proves that superposition is an incredibly accurate and reliable tool for dissecting multi-source linear networks. All right, so next moving on to chapter 5, which converts capacitance and inductance. So let's look at question 7. We are presented with a more complex bridge like a network containing multiple energy storage elements and 3 capacitors and 3 inductors driven by a 4 milliampere and a 1 milliampere current source. So the goal is to determine the DC the steady state voltage across that far right 1 micro F capacitor. So under the DC steady state condition, an important physical transition occurs. So all capacitors act as open circuit because they are fully charged and block the DC current. So while all inductors act as the ideal short circuits because the current is constant and no voltage is induced. So when we redraw the circuit applying these rules, we find that the current passing through the upper loop I1 is 4 milliampere and the lower loop path I2 is 3 milliampere. So by using the Ohm's law across the vertical 20 kilo ohm resistor, the voltage drop is calculated as 4 milliampere times 20 kilo ohm plus 3 milliampere times 20 kilo ohms. So which simplify to equals to 80 volt times 60 volt. So and after that we can get a final value of 140 volt. Right, so next we simulated this circuit in PSpice using a bias point analysis to check our steady state assumption. So looking at the simulation data readout, the voltage at node 131 is locked at exactly 140 volt because the inductors behave as a short circuit and this voltage transfer perfectly across to our measurement node. Alright, so in conclusion, our manual analysis and PSpice simulation are in perfect agreement at exactly 140 volt. So this successfully demonstrate that replacing capacitors with open circuit and inductors with short circuit in an accurate. So fundamental method for evaluating the long-term DC behavior of complex reactive circuit.
For the question of chapter 6 is to find I for t greater than 0 if the circuit is in steady state and t equal to 0 minus. First, I will explain the manual calculation first. Before switching t less than 0, the circuit is in steady state, so the indicator we have like a short circuit, and then the 6 ohm resistor is in parallel with the 12 ohm resistor, so we can get the resistor is 4 ohm, and then we add a 4 ohm resistor in series. 4 plus 4 we get a 8 ohm, and the last Req is equal to 8 ohm in parallel with 8 ohm, so we get a Req is 4 ohm. Since the both branches have the same resistance, so the 6A current source can be divided equally. So using the current division rule, I1 is equal to 6A multiplied with 8 over 8 plus 8, we get a I1 is 3A. Next, we calculate the initial current flowing through the inductor branch. I0 minus is equal to 3A plus 12 over 6 plus 12 is equal to 2A. So we get a I0 minus is 2A. And then we have to find RTH now. RTH is equal to 6 plus 4 in parallel with 12. So we can get the final RTH is 9 ohm. Next, we calculate the time constant, we use the formula tau equal to L per RTH. So we can get the final answer is 1 over 18s. And finally, we substitute all the values to find the IT, and then we can get the IT is equal to 2e to the power of negative 18t. For the simulation part, we use PSPice to build the same circuit. The current probe was placed at the inductor to observe I. From the graph, the current starts at 2 ampere and decreases until it becomes almost 0A. This matches with the manual result because our equation also show the currents decay from 2 ampere to 0 ampere. Next, I will explain the comparison and discussion. First, we compare the results from the manual calculation and the PSPice simulation. As shown in the table, both methods produce the same initial current of 2 amperes. This means the manual calculation is consistent with the simulation result. For the discussion, before switching, when T is less than 0, the inductor behaves as a short circuit because the circuit is in DC steady state. So the initial current is I0 minus is equal to 2 amperes. After the switch closed at T equal to 0, the 6A current source is isolated, and the energy stored in the inductor begins to discharge through the equivalent resistance. Using the time constant formula tau equal to L per RTH, we obtain that IT is equal to 2e to the power negative 18t amperes. So this equation shows that current decreased from 2A to 0A, which match the simulation graph. Therefore, we can conclude that the manual calculation and the simulation agree with each other. For chapter 7, we need to find IO if the source current is 5 cos 10t plus 40 degree amperes. So the angular frequency is 10, and we convert the source into polar form, we can get IS equal to 5 angle 40 degree amperes. Next, we calculate the impedance of the inductor and capacitor. We use the formula ZL equal to J omega L, so we can get the ZL is 2J, and the ZC we use the formula 1 over J omega C. Okay, we can get the answer is negative J. Okay, next for the left branch, 4 is in parallel with 2J, so we can get a Z left is 0.8 plus 1.6 J. For the right branch is 3 minus J. So the total impedance is Z left plus Z right. So the total Z is 3.8 plus 0.6 J. Okay, last we use the current division to get the IO. So we can get the IO is 2.33 angle 94.46 degree amperes, and then we convert it to the time domain. 2.33 cos 10t plus 94.46 degree amperes. Next, for the simulation part, we build the same AC circuit in PSPice. We use AC swipe analysis to observe the output current through the capacitor branch. At the operating frequency, we use 1.592 Hz, and the simulation result was show that IO is equal to 2.3249 angles 94.46 degrees ampere. So this result is very close to the manual calculation, and the graph also show the magnitude and phase of the output current at a selected frequency. Lastly, I will explain the comparison and discussion. From manual calculation, we get that IO equal to 2.33 angle 94.46 degree ampere. From PSPice simulation, IO equal to 2.3249 angle 94.46 degrees ampere. The magnitude values are slightly different because of rounding during manual calculation. And for the phase angle is exactly the same. It was 94.46 degree. So the phase error is 0%. Therefore, both manual calculation and PSPI simulation show excellent agreement. This proves that the analysis method is correct, and PSPI successfully verifies the theoretical result for this AC circuit.